Now, in order to determine the exact future amount, or at least get an expression that indicates the exact future amount, we might have to approximate that because it might be an irrational number. What we want is a graph of the rate at which future value accrues. Then, if we integrate that rate over time, well, what's the meaning of a typical trapezoid? Well, we want to think in terms of thin trapezoids. The area will represent of course average altitude times width, and that's going to be the average rate, the average of the altitudes. The altitudes would then represent rates at which future value accrues. So it would be average rate times time interval, and that would be the contribution to the total future value. So what we're going to do is we're going to say, okay, let's just say we've got this divided into a bunch of trapezoids. So let's just take the area of a typical trapezoid between time t and time t plus delta t. Okay. There's time t plus delta t. We're going to assume that instead of flowing into the account in discrete amounts of $500 every month, let's assume that we have a $6,000 a year contribution. So the rate at which future value accrues will depend on the $6,000 constant $6,000 a year flow of money into the account, and a continuous constant continuous $6,000 a year flow. Okay. Then we ask ourselves, well, for a typical interval here, how much money flows in? And then for a typical interval, how long does it have to accumulate? Because we have intervals here, we would have intervals over here that would have longer to accumulate. We might have intervals, we will have intervals over here that have less time to accumulate. So if we were to divide this graph up and approximate the area by the areas of a bunch of trapezoids, trapezoids closer to t equals 0 will have longer to accumulate interest than trapezoids close to t equals 20. And of course, we understand that perfectly well in terms of what we've done previously. So we want to get a handle on this. So we're going to develop this.